everyone, I'm Ashok. Welcome to a series of tutorials on neural networks. And the tutorials assumes no prior knowledge of neural networks. So I'll start with beginning. And then as we move on, I will explore all the advanced neural networks, including deep neural networks and other types of neural networks, including convolution neural networks, recurrent neural networks, and LSTM, which is long short-term memory neural networks, and how exactly it works. Also, in this series, we'll explore concepts like how a network gets optimized using stochastic gradient descent, what is backpropagation, how exactly it works, with a more practical and taking numbers and examples. In this video, to begin with, I will start with a very simple idea of neural network. What exactly is a neural network? Where do you apply and how does it work? So for this, let's take a very quick example of apartment pricing. So let's assume that there are a few apartment prices available for us. So I'm going to say area of the apartment will be in square feet. And then you have your price in US dollars, or simply US dollars in $1,000. And this is your input variable X, and this is your target. For simplicity's sake, taking only one input variable. And then let's speculate some prices. A 1,000 square feet apartment is costing you $500,000, and a 1,500 square feet apartment is costing you, let's say, $700. Okay. If you try to draw this graphically, this would be just two dimensions, so it'll be easy for us to demonstrate. This is area in square feet. I'm gonna just take 1, 2, 3. So these are not to the scale, so we will not expect a very accurate, but you get an idea of it. And this is your price. So let me take 1, 2, 3, 4, 5, 6, 7. Okay, let me just extend a bit. 8, 9, for example. So this is 100, 200, 300 US dollars, $1,000, 400, 500, 600, 700. So those are the numbers we have taken. And this is a million. Sorry, $1,000, which is of course a million. All right, so I'm going to just draw a quick grid lines for our easy understanding. Oops. I should have drawn this grid before the lesson starts. My apologies. Okay, so now we have a grid. So I'm going to simply go ahead and plot these two things. So this is your 1,000 square feet apartment costing you $500,000. So this is the point. Okay, and there's another one which is 1,500 square feet and it's costing you this one. Okay, great. So wonderful. So I want to fit a line to this because it's 2 points. If you want to draw a line passing through, the line would be something like this. For example, let's say something like this. Oops, okay. Let me take a different color. That's a blue itself. And let's do, okay, that's good. Okay, so that's your line. And what's the benefit of drawing a line? Because now this line passes to the two other points we have. We can use it for prediction. For example, now if I want to predict for 2,000 square feet apartment, for example, what would be the price. So I can simply go ahead and say, hey, this is 2000, and this is where it is actually interacting. So there'll be somewhere between 880 or something. So that can be done visually. If you want to do it mathematically, you need to start with a simple line equation. A line equation uh, is y is equal to mx plus c. I'm pretty sure you know this from your high school mathematics, where m is a slope, which is telling you how tilted it is. It's a tan of the angle towards the x, and then c is your intercept. So m is slope, and c is your intercept. So we call it as y-intercept, which basically this is intercept. So this is where this line interacts with your y-axis. In our case, our y-axis is price. So in our case, it's actually y-intercept is actually our price axis intercept. So if you put both of these points into, let me just make it a little smaller, make some more space. All right. So we know that this is y is equal to mx plus c. I have 2 points. One is 1,000 square feet apartment costing you $500,000. So I can simply say, I can say mx plus c is equal to y. Both are same. Now this looks a little better. So I don't know what is m. So x is 1,000 plus c is equal to my y is $500,000. And then you have the second point, which I'll write it above. Just rubbing this off, make a little space. Okay, and then the second one is 1,500 square feet plus is equal to 700. So it looks familiar. We have two unknowns and two equations. So we can solve this, isn't it? It's a simultaneous equation. Again, high school mathematics. So just subtract this equation from this equation. You'll end up getting 500m, and your c get cancelled. C minus c is 0, and you get 200 over here. So resulting m is equal to 200 by 500, which is essentially 2 by 5. 2 by 5 is 0.4. So now that we have m is equal to 0.4, we can put this m value in any of this equation. Let's say I'm going to put in this equation. So m is equal to 0.4 into 1,000 plus c is equal to 500. So it essentially is c is equal to 400, because 0.4 into 1,000 is 400. So you'll take that 400 that side. 500 minus 400 is equal to 100. So c is equal to 100 and m is equal to 0.4. Brilliant. So my equation is now has become something like this. So it's actually 0.4 m. So m is 0.4. So 0.4 x plus 100, because c is equal to 100, is equal to y. And this is our line equation now. So this is my line equation. So if you give me any apartment price or area in square feet, I can predict the price by using the simple line equation. Let's put our 2,000 square feet apartment and see how much we are getting. So if you put 2,000, take it back. So if you put 2,000, so it's actually 0.4 into 2,000 plus 100 is equal to your price, which is y. So this is, how much is this? It's, 800 plus 100, which is actually 900. So, well, my diagram is almost as actually it is perfect. It is actually touching at 900. So 900 is a price. So it's calculated to 900 now. Brilliant. So this is super simple because we have two apartment prices on which we have drawn a line, and mathematically we solved it as well because they are simple two simultaneous equation, two unknowns. We found what is the slope, what is the intercept, and we got the line equation, which is 0.4x plus 100 is equal to y. And any apartment price you put in x, you get a price of the apartment, which is y. Great. So I hope this is pretty straightforward. But what if you have more than 2 points? For example, same example, Now let's assume that you don't have all of this. You have one more point given to you. So I have another point which is 1100 square feet, which is in another apartment price. The data is available and that's costing you, let's say, $600. So if you try to plot this in this, so you have another point which is 1100. So somewhere here, I guess. Oh, let's use blue color. Somewhere here. Scale does not matter. That's okay. And this is 600. So if you look at this, these 3 points are not in straight line. So if I try to fit a line, well, I can actually draw a line which is kind of like doing it. I cannot fit one single line for these 3 points because it's not in a straight line. So what I can do, I can actually fit a line something like this, for example. Okay. And this line is called as best fit line. This line is called as best fit line. Okay, it's still the same equation, mx plus c is equal to y. But m and c cannot be simply calculated by what you have done before mathematically because it is not mathematically solvable. You will not get a solution at all. Instead, what you can do, you could actually try to find the best possible m and c value, slope and intercept, which satisfies this equation in a best possible way. How do you do that? Well, we shall actually find out the errors of this is your error 1, for example, because let me just zoom it a bit. So this is your error 1, which is corresponding to the error of the first point. This is your error 2, and this is your error 3, which looks very, very, very small. All right, and then we try to create an equation which kinds of sums up all of these errors. Okay, and these errors can be negative and positive. So what we can do is we can take an absolute values. If we do that, we say L1 cost function or loss function. So let's take a square of it. So I'm going to take E1 square plus E2 square plus E3 square. The reason I'm taking square is just making sure that the errors are taken care, as well as I'm giving more importance. Errors are severely penalized because you're taking the square of the error. A small error will reflect into square of it exponentially. All right. So and this is called as L2 loss function. In fact, this is called as loss function. I could also say it as cost function. The goal is to minimize this cost function. Okay. And for doing that, we should be tilting this line in such a way that your square of the sum of the square of the errors are minimum. Okay. So if you look at it in a very high level, in a simple boxes, let me just hide all of this. All right, so that's it. That's the idea of fitting a line, or basically fitting an equation to your data, and thereby you can predict your price. So if you visualize in a very high level, so what we have done is simply x, and you're given to some kind of mathematical equation, and then we got a y, and this equation is mx plus c, the line equation. So we are fitting a simple. This is actually a linear regression model. So for simplicity's sake, for calculation, I'm going to take simple values rather than taking thousands and hundreds. Let's say 500 square feet could be simply 5, and let's say it costs you about $200,000. Put 20 there, and then this is like, let's say 350 or 35, and uh, in neural networks, the mx plus c, m can be called as actually wx plus b, where w is your weight and b is your bias. So it makes sense because w is actually multiplying it, it's a weight, and b is offsetting it, biasing it. Okay. I want to I want to find the W and B value, not by mathematically solving it, because if you have two data, of course, you can simultaneously, you can solve it mathematically. If you have 100, 1,000 records, a million records, obviously, you're trying to fit a line or, in a simple manner, and calculate the W and B in such a way that you reduce the error, which we saw that as a cost function. So I'm going to simply take W is equal to 2 and B is equal to 5 for simplicity's sake. And let me, the equation Wx plus B is equal to Y turns to be 2x plus 5 is equal to Y, isn't it? And they put the first value, x is equal to 5, so it becomes 2 into 5 plus 5, which results in 15. Okay, and the next value is 10, so it's a 2 into 10 plus 5 is equal to 25, but the actual values are 20 and 35 correspondingly. So if you look at the error in this case is defined as actual value minus the predicted value, which can be represented by y cap. In our case, the actual value, error is equal to actual value minus predicted value. In our case, actual value is 20 and the predicted is 15. The error is 5. In the second data, actual value is 35, predicted is 25, error is 10. Let's take an average of it, average of all the errors. We can also take a square of the errors. That becomes MSE, mean square error. What we're going to take is mean absolute error, which is L1 cost function. So we simply say 5 plus 10 by 2, which is 7.5. Great. So this is quite some error, and I want to see now. I want to change the W's and B values and see which is the best W's and B value, which is giving the minimum error. First, I would like to reduce the W and B, or let me just reduce only W, keeping the B constant for simplicity. I'm going to make W is equal to 1 and B is equal to 5. Remember, W is equal to 2 and B is equal to 5 taken randomly, called as random initialization. All right. I've taken a value, simple values, but typically the values are between minus 0.5 to plus 0.5. And this is a complete whole theory on how do you randomize, because your network performance or the optimization of this particular simple network depends on your random values in the beginning when it gets complex. But for now, it's a simple network, so I'm going to take 5 as a random start. I got a value of 7.5. Now, if the W is equal to 1, my equation becomes just x plus 5 is equal to y. Put those values. 5 plus 5, which is equal to 10, and then this is actually 10 plus 5, which is equal to 15. Okay, and we will calculate the error values. So error values, in this case, it's actually 20 minus 10, which is 10 is the error value. For the first data, the second data is pretty high, 15, 35 minus 15 is 20. Take an average of it. 10 plus 20 by 2 is 15. So the error has increased. So taking a W, a lesser value, increases the error. It's not good. So I want to let's say the other side. So let me increase the W value by 3. Okay, let's keep the B as same as 5. Now my equation is 3x plus 5 is equal to y. X is equal to 5. So 3x plus 5 is actually 20. And the second data, 10 into 3 into 10, which is 30, plus 5 is equal to 35. Well, I've taken a values in such a way that it actually converges quickly. So now you can see that the errors are actually perfectly same. So there is no error, 0, 0. Error becomes 0. So in this case, increasing the W actually reducing the error. In a similar manner, you need the network actually sees which direction is actually helping us to increase and decrease. And this is actually called as gradient descent. We will have a complete different topic on that. But just to give an idea, so by doing this, your network optimizes your W's and B's. Now that we have W is equal to 3 and B is equal to 5, I can simply state this equation as 3x plus 5 is equal to y is your perfect equation for this data or for this data. Okay, and give me any x value, boom, I get the price of it. It's a very simple network. Okay, if you want to, because it may not be actually fitting all of the data because there's just two information, but you have a lot of data, this might not be fitting it. Taking the same idea to the next level, let's say you have uh, well, just to summarize the previous one, so this is nothing but a 3-node network. So I can simply write this as x is your one node, and then this is actually a kind of hidden node. So it's a hidden node, and then you have y as one. So it's actually a simple one-node network. In fact, a simple linear regression can be taken as a simple one-node neural network. So it's one-node neural network with one layer, one node, one input, and one output. Now I'm going to delete this and say that I have two inputs now, x1, x2, and then let's assume we have three hidden nodes. So this actually three hidden nodes, b1, b2, b3 are biases of individual nodes, for example, and then you have one output. Just keep it that simple as one, y. Okay, and then this is your x1, x2, and stuff like that. So the network has suddenly become a little little complex. So if you want to calculate this same idea of multiplying the weights and adding the biases, network now looks like this. Let me take one color for this. So you have to actually multiply x1 with three weights and the corresponding biases. So let me call it as w11, w12, and w13. The one subscript corresponds, that belongs to your first input, and the next one is actually which hidden node you are actually multiplying that way. And the second one, let me take another color for that. So I call it this as w21, w22, and w23. And of course, all of these three signals combined will, and then finally that results, the summation of this results in y. Okay, so writing down the equation, so if you apply the same concept of x w plus b is equal to y, in this case it becomes like this: x1 plus x2 plus your b1. Okay, so I'm going to use the same colors so that you can relate that. 1, 2, and then you have b is equal to, so that actually becomes your first signal. So this is the signal I'm talking about. So I multiplied x1 with w1 plus x2 w my apologies, it's 2, 1. It should be it's whole different color. So let me get that color. 2, 1 plus b. Okay, that brings up this signal. So x1 w11, which is this term, x2, this is x2, x2 w21. So this multiplied by this multiplied by this plus b1 will result in this signal. In the similar manner, I'm going to write down the other two, x1, x2, x1, x2, and then these values w12, w13, and then these values, these corresponding weights 2, 2, 2, 3, and then you have biases b1, b3, sorry, b2, and this results in your y. So essentially, it's the same concept of x into corresponding weights plus bias results in your output y, because we have three hidden nodes, three nodes in your hidden layer. So that the same concept expands to what is shown in this equation. This can be further generalized into a matrix notation, because this can be written as x1, x2 as x1. Let me just make it a little smaller and push it up. Okay. So x1, x2, okay, and then you have this weights matrix. So let me just put them in W11, W12, W13, and there is this one, W21, W22, W23. Okay, I'll use this color. Plus your B1, B2, and B3 is equal to your Y. If you look at it, matrix multiplication. So this matrix is one row, two column, and this is actually two rows, three columns. If you multiply that, it results in one row, three column matrix, which can be added to this one row, three column matrix, which finally results, we sum it up into Y. So it's again transforms to something like this: X into W, for example, plus B is equal to Y. So X, W, B, and even Y if you have multiple outputs or matrices. And essentially what we do is to find out the right values for W's and B's by optimizing, looking at the errors. So we keep on changing the W's and B's and try to find which W's and B's is giving a minimum error, which is a minimum cost function, and thereby we optimize the network. Once the network is optimized, when you give a new input, X1 and X2 in this case, will give you predicted output, which is your Y. And this network is actually two inputs, three hidden nodes, and one output network. So I hope that explains the concept. All right. And if you want to increase the network complexity, we can increase the number of nodes in the hidden layer, and thereby you can also increase number of hidden layers, and thereby the network complexity increases, which means you have more W's and more B's, and finding the right values of W's and B's will basically optimize the network. And by this, the network can learn more complex patterns in the data. I'm going to quickly implement this in one of our popular Python packages called scikit-learn, sklearn. The simple network, sklearn is good enough. When you go for deep learning and other networks, TensorFlow Keras is more easier. In fact, TensorFlow 2.0 comes up with the Keras inbuilt. It's so easy. A non-developer can learn it and do neural network fitting. But let's go to the okay. So I'm going to import. I assume a bit of prior knowledge, and if not, please watch the other videos which talks about the basics of sklearn and all of these machine learning algorithms. So neural networks, import MLP, which stands for multi-layer perceptron. I'm looking at regressor over here. I'm going to define the X and Y, the same values. So X is always multi-dimensional because you have more than one X. So in the first example, you have taken X is equal to 5 as one input and 10 as another input, and the corresponding Y's were 20 and 35, if I'm not wrong. Okay, I'm going to initiate this model, say MLP, okay, regressor, and then let me say hidden layers is only 3 because that's what our diagram is. So we have 3 hidden layers, hidden layers node 1, 2, 3. So one hidden layer, 3 nodes in the hidden layer. If you want multiple hidden layers, we can put a comma and put the hidden layers next. So right now I have one hidden layer which contains 3 nodes. So I can simply say hidden layer sizes. I'll give a tuple with just one 3 as a value. Now I'm going to say model.fit X and Y, and that's it. Well, it doesn't reach the convergence because it's only 2 data. So normally you have hundreds and thousands of records minimum required to fine tune a neural network. So I'm going to increase the maximum iterations with a crazy number of values. Let me say I'll put some, let's say 3000 because it's really small data. Yeah, it converged. Okay, so now I'm going to predict, for example. So I'm going to say predict I'm going to give a value of input value of 20 and see what comes out. Something around 70, 65, 63. So 63 is a predicted value for given 20 as an input when the network is trained with the training data of x is equal to 5, 10, and the corresponding value is at 20, 35. Brilliant. If you want to look at the weights and biases, you can by just typing in model dot coefficients, and that gives you the weight matrix. So this is actually, let me print it nicely. Oh, okay. So this is one array and this is another array. It's a list of two arrays. So I can actually make it as numpy array, but so this essentially this is your so this is your these are your W1s, W11, W12, and W13 values, and these values are your W21, W 22, and W23. So this is a matrix which is being given as a coefficients or weight matrix from our model. And for biases, you can simply type in model dot intercept. So the name is written. So these are your B1, B2, B3, and this is the bias of the last layer. So this is a very simple neural network with 3 hidden nodes and 2 input values, 2 input variables, and 1 output variable. So that's the idea of the neural network. The whole challenge here is, of course, how do you get these W's and B's? And there is a whole lot of theory behind it. We use gradient descent algorithm to find the W's and B's with the minimum possible time and minimum computation. And we also have stochastic gradient descent, which basically randomly tries to club the number of records and finds the best W's and B's. It's much more faster than a traditional gradient descent. We will talk about all of this in the future videos. And for now, hope this is helpful. Let me know in the comments. If you don't understand any concept or if you have any clarification questions, I'll be more than happy to answer them. That's it. Thank you very much for watching this video. And if you like this initiative of this channel, please subscribe to the channel and also click the notification button. I'll see you in the next video. Thank you.